In 2017, a research paper introduced a new AI architecture that changed everything. It became the foundation for modern chatbots, large language models, translation systems, and even image generators. That architecture was called the transformer. But what exactly makes transformers so powerful? Before transformers, AI models processed language using sequential systems like recurrent neural networks. These models handled words one at a time, which made them slower and less effective at understanding long sentences. Human language is complex. Words depend on other words across long distances. To truly understand meaning, a system must evaluate relationships between many words at the same time. Transformers introduced a radical idea. Process the entire sentence simultaneously. Instead of reading left to right step by step, the model analyzes every word in parallel. At the heart of the transformer is something called attention. Attention allows the model to determine which words matter most when interpreting meaning. For example, in the sentence, "The animal didn't cross the street because it was too tired," attention helps the model understand what it refers to. Self-attention means each word looks at every other word in the sentence. It assigns important scores to build contextual understanding. These important scores help the model weigh relationships between words, allowing it to capture meaning more accurately. Inside this process, each word becomes three mathematical vectors: a query, a key, and a value. Queries compare against keys to calculate attention scores. These scores determine how much influence one word has on another. The model then creates weighted combinations of values, producing refined contextual representations of each word. Transformers use multi-head attention, meaning several attention mechanisms operate in parallel. Each attention head can focus on different aspects, such as grammar, context, or long-distance dependencies. Because transformers process words simultaneously, they need position encoding to understand word order. Position encoding injects information about sequence structure into the model's internal representation. After attention, word representations pass through feed-forward neural networks that extract deeper patterns. These layers are stacked repeatedly. Each layer builds more abstract and refined understanding. Original transformers used an encoder-decoder architecture. The encoder processes input. The decoder generates output. During text generation, the model predicts one token at a time based on all previous context. Scaling transformers to billions of parameters dramatically increase their capabilities. More parameters mean more pattern storage. More training data means broader understanding. This scaling led to emergent abilities like reasoning, summarization, and translation. Transformers now power chatbots, coding assistants, search systems, and recommendation engines. The architecture has expanded beyond language into vision, audio, and multimodal systems. Despite their power, transformers require massive computational resources to train. Inference also consumes significant energy, especially at large scale. Transformers operate within context window limits, meaning they can only process a fixed number of tokens at once. Because they predict probabilities rather than retrieve facts, they can generate confident but incorrect outputs. Alignment techniques and fine-tuning help improve safety and reliability. At their core, transformers are advanced pattern recognition engines trained on enormous datasets. Ongoing research focuses on efficiency, longer memory, and improved reasoning structures. Transformers redefined artificial intelligence by mastering attention and scalable parallel processing. They became the engine behind modern generative AI, shaping how machines understand and produce language today.